try to talk about a little bit of cryptography in general and some that showed up in the movie obliquely. Oh, by the way, my name's Reid at the math department at Missouri State. All right. So the first thing I want to talk about just a little bit is about the accuracy of the movie, which you sometimes hate to quibble with such a great movie where they had to take dramatic license to make things work, but it's part of my job. So the first thing is they sort of made it sound like nobody had been able to do anything with Enigma, but Polish cryptanalysts had been able to break it in 1939, an earlier version, and based on some bad things the Germans were doing that made the codes easier to break. But then the Germans changed the machine and got rid of their bad practices, and so then they were back to square one, but it wasn't as if nobody had done anything. They also had built a machine not quite as powerful as Christopher that they called a bomb to help decrypt things.
And Turing had knowledge of that?
Yes, yes. Oh, in fact, and please feel free if you have any questions to stop me and ask.
They showed two Enigma machines there. The first one was the one that the Poles decrypted, which was a three-rotor machine.
Right.
The second machine they showed was a four-rotor machine, which was the one that was developed by the German Navy, which was Turing's job.
Right. So the machine that we're talking about at Bletchley Park is also called a bomb in honor of the Poles. So yes, he was aware of their work. In fact, he was building on their work, and unfortunately was not named Christopher. Turing was not involved in the life and death decisions that they depicted in the movie. He just broke codes. Whoops, and most importantly, from a mathematical point of view, at one point, the Keira Knightley character is talking about Euler's theorem, and to a mathematician, that's it's like fingers on a chalkboard. So Euler, not Euler. A few things I noticed in the movie this time that I wanted to point out. At the very beginning, when at the very beginning when the police came to his place, he was sweeping up cyanide. In fact, when he committed suicide, he used a cyanide-laced apple and took a bite of it, and that's how he. So it was, I think, the movie makers doing some foreshadowing that, for those who knew. Turing actually did speak German, or at least he knew some German. And the crosswords that they talked about in the movie, those aren't American crosswords. They're British-style crosswords, which have a lot more wordplay. At least I think they're much more difficult than American-style crosswords. So to be able to solve these things in 6 minutes is really amazing. All right, let's continue on and talk a little bit more about cryptography. There are two basic kinds of codes, private key codes and, as we'll see later, public key codes. The key is the secret to how you decode things. In private key, as in the Enigma, as we'll see later, the settings are secret. You don't want anybody to know what the settings are, because otherwise you'll break the code. The first kind of private key code we're going to talk about is monoalphabetic. Monoalphabetic means one letter in gives you one letter out. And the most basic one is called a Caesar shift. Caesar is after Julius Caesar, who used a similar thing in Roman times. And it's a little hard to see for me. So the Caesar shift is you shift a certain amount forward in the alphabet. In this case, 3 letters. So A goes to D, B goes to E, etc. W goes to Z, and then where are you going to send A to A, and then finish it off with BC. All right, so computers deal with things, with numbers. So instead of doing everything in terms of letters, I want to translate letters into numbers, and you may think the obvious thing would be to make A1, B2, and Z26, or Z, if we're being British. But it turns out for what we want to do, it's going to be slightly different. We actually want A to be 0. Have A be 0, B be 1, and go up to Z equals 25. And then what does the Caesar shift look like? numerically, 0 goes to 3, 1 goes to 4, 2 goes to 5, et cetera, et cetera, et cetera. Well, if you look at the first couple, what does that look like? What are we doing arithmetically?
+3.
We're adding 3 to everything until we get down to here. 23 plus 3 is 0. So it turns out that I beg your indulgence. I want to teach you a little bit of math. Modular arithmetic. I heard some people in the audience are even saying it. So modular arithmetic is like ordinary arithmetic, but with a twist. If you add x plus y mod n, where n is some number I'll tell you about, you get the remainder when you divide x plus y by n, and similarly you can do multiplication. So for example, 3 plus 5 mod 6. Well, 3 plus 5 ordinarily is 8. And 6 goes into 8 once with a remainder of 2. That's why 3 plus 5 is 2. You can also do multiplication. 3 times 5. That's 15 in real life. 15. 6 goes into 15 twice. And that leaves a remainder of 1.
3?
Yes, so there's a typo on this sheet. And that 1 should be a 3. Yeah. It's not the new math. Finally, one more example, 7 times 4 mod 9. It's 28 divided by 9. 9 goes into 28 3 times. And you get a remainder of 1 that time. Oh,
Remainder of 3.
now it's changed with, I am not a PowerPoint expert, as you may have gathered. So a typo creeped in there somewhere. Okay, so with this interpretation, how can I describe the Caesar shift mathematically? If M is the plain text, unencrypted thing, and C is my encrypted message, then we get that previous thing by doing M plus 3, but doing it mod 26. How will we decode? How do I undo this? Well, if I encrypt by adding 3, I'll decrypt by subtracting 3. And in fact, that's what we do. All right, so that's fairly straightforward. And I should have just said this earlier. When the boys were communicating in school, I checked, and they're using a Caesar shift. If you actually, I got a red box. I rented it. I freeze framed it and checked. And in fact, they were doing Caesar shift. They were shifting by a certain amount in the alphabet every time.
Specifically 3?
Oh, no, it's just no, I think they went back 4 for one of them, and I checked it. But we'd like to get a little bit more sophisticated. Oh, and also this modular arithmetic I'm telling you about is going to show up later in the talk. I'm not just torturing you. So, or maybe I am. I don't mean to be torturing you. So you can do slight variance. In the Caesar shift, you just add. So now instead of just adding, I want to do somebody said a stretch factor. So if I do 3m plus 10 mod 26, if I take k, if you look at the thing that numerically corresponds to 10. So if I multiply by 3, I get 30, add 10, I get 40. 40 mod 26, 26 goes into 40 once with a remainder of 14, and that corresponds to the letter O. So k would be encrypted as O. So that's another way that you can use modular arithmetic to get these monoalphabetic codes. But you don't need to use any of these formulas at all. Whoops, sorry, decrypting. How do you decrypt? Subtract 10 and multiply by 9 and do it all mod 26. You can do arbitrary permutations, anything you like. So I'd start sending A to M, B to O, C to X, D to I, E to E. And then whatever I want, any scrambling of the letters I want. How many ways can I do this?
26.
Yeah. Well, so some people already know the answer. How many choices do I have where I send A?
26.
I have 26 letters. But then once I send A to one letter, I can't use that letter again. So for B, I would only have 25 choices. C, 24, et cetera, et cetera, et cetera. Each of those is independent, so I'd multiply them together to get what somebody said, 26 factorial for those in the know. That's 26 times 25, all the way down to 2 times 1. I got a computer to tell me that's what it is. And also as part of teaching science, big numbers like this are a pain to actually write out explicitly, so we'd rather use scientific notation where you write down the first digit and then how many decimals there are after it as an exponent. In this case, there are 20, after the 4, there's 26 decimal places. So it's 4 times 10 to the 26, which is a more compact way of writing things. All right. So in theory, there's this humongous number of possible permutations that we could do to encode things. So like, forget Enigma, this seems like a really, there's a jillion different ways to decipher. How can I figure out? How can I break these codes? This seems like it's impossible. But somebody said something. Frequency analysis actually makes these trivial. These are trivial to break. In English, E is the most common letter, then followed by T, A, O, I, N, shrewd, blue, a whole bunch of things. And here's a little frequency table. It's got a very sharp peak at E and then falls off. So if I get this, if I have a secret code and I have a Q, the Q shows up the most often, what's Q almost certainly an encoded version of? E. The second most, T. If you keep on doing this, after a while you'll get enough stuff that you can start filling in the gaps. The word T, H, E blank, E is going to be there or these, depending on what. But you can start guessing what things are. It's pretty easy to do. So the moral of this story, which is going to show up over and over again, is it looks like, if you just count how many possible codes there are, it just seems completely daunting. But by using underlying structure, in this case the frequency of English, you can actually solve this quite easily. Then for monoalphabetic codes, it doesn't take very long. In fact, every day with my cup of coffee, I sit down and do the crypto quip in the news leader. And usually that's only 2 sentences long. It also has the advantage it's broken up into words, which makes things a little bit easier, but they're really not difficult to do. So monoalphabetic, not very good. So we're going to move to polyalphabetic. Polyalphabetic allows more flexibility. The same letter will not necessarily be encoded the same way every time. So we want to get rid of things. So one way of doing this is to use the polyalphabetic codes, which I just said can be done different ways. So the way we're going to do this is to choose some keyword, repeat that underneath our plain text. I'll put a slide up in a second. And the idea is each letter of the key will tell me how much to shift each letter. So an example with the the name of this particular cipher is Visionaire. So meet, it's not meet noon, it's meet me at noon. And I'll choose Moxie as my code, repeat it as many times as I need. And so now, how's this going to work? I'll actually put the numbers in a second. So M corresponds to 12 in our numerical system. So that means I'll shift the M in meet 12 letters forward. That's what I'll encode. The E, I'll shift whatever O is forward. Oh, in fact, what am I guessing? I've got it right there. So I've translated the plain text into numbers and the key into numbers. And then what's the Caesar cipher do? You add, right? If I want to see what 12 gets encrypted as, I add 12 to it and do that mod 24. So for most of these, it's just ordinary arithmetic. 12 and 12 is 24, 4 and 14 is 8. They're in the fourth column. 19 and 8, in real life, that's 27, which mod 26 is 1. And then, just to get it back into English, do this. So look, what's happened here? There are a lot of Q's. Oh, but do we then, can we conclude, oh, there's a bunch of Q's, those must be E's? No. So in fact, we have 3 E's in this message, and they're all encrypted as different letters. So, and we have 2 N's, they're also encrypted as different letters, and 2 O's that are encrypted as different. Anyway, what does this do? This smears out the frequency. So you're not going to have that sharp peak, it's going to be a flatter curve, and our frequency analysis, at least our naive frequency analysis, will not be so helpful. Whoops, wrong thing. that just is repeating what I just said. So the French, who, well, this was invented several times in history, but the French reinvented in the late 1800s. They thought it was unbreakable, and they called it, my French is terrible, the chiffre indéchiffrable, which means unbreakable code. But we wouldn't be watching this exciting movie about the Enigma if the Vigenère thing was the bee's knees. Frequency analysis strikes again. So what we're going to do is guess the length of the key. And we'll make repeated guesses. We'll just call that L. And what I'm going to do is now take every elf letter in the message and then do a statistical analysis on that. Now, what's going to happen if L happens to be the length of the message? The length of the message, the length of the key. So like if it was 5, I'd have M every time. So all that part of the text would be encoded the same way. In fact, it'd be just a single Caesar shift. So the distribution of the encoded things would look like English. So if you actually had the length of the key, or a multiple of it, the encryption is just a Caesar shift. Everything would be going in the same way. Everything would be shifted by M. So E's would show up in the encoded as frequently as E's do in English. And so you'd get, if you did a graph of this, you'd get a graph like the graph I showed at the beginning with a sharp peak and then a tail out. What would happen if I didn't pick the length of the letter, the length of the key? It'd be flatter. Does that make sense? Because then you'd be encoding the same letter different ways. So if you didn't pick the length, if you didn't have the length of the key, your statistics would be flat. And so they would say, that's not the length, try something else. You would do this until you got a sharp spike that would tell you that you found the length of the key. Once you've got that, standard frequency analysis does it, and it's done. So contrary to being an unbreakable one, this is only slightly more difficult than monoalphabetic code. So, but let's see. So what would make life harder? Oh, sorry, I should point out, monoalphabetic, 2 sentences in the paper, you can break it. You need more data in order to break these polyalphabetic codes. Okay, the Enigma. So there, as was mentioned earlier, there are various versions of this. One version had 3 wheels, which you choose from a set of 5. And essentially what each of those did would generate a Vigenère cipher. But instead of a key of length 5 or 6 or 7, the key is length 17,576. That's long enough to pretty much defeat any of these statistical analyses. Also, as you saw in the movie, at the front of the machine, there were 10 chords that you would attach in pairs to transpose letters to make life even more complicated. Now let's see if my numbers agree with the movies. Oh, we don't. So the movies kept on saying 1.59, I think. And I and somebody else think it's 2.6. Probably because it's a different version of the machine. The one in the movie is a different one than the one I'm talking about. Anyway, it's still a ton. Whoops, ack. Whoop, there we go. Oops, nope, further back. Sorry. Okay, that's a lot of settings to check. But so the idea is, if it were a complete black box, if we had no idea about the inner workings of the machine, then the fact that it's a Vigenère with this huge length would make it almost impossible to analyze. But the Allies did have an Enigma machine. They knew how to analyze it. The only thing they needed to figure out was what the settings were. Now, of course, there's 2.6 times 10 to the 19th settings, and that's a lot. So I think the movie maybe played a little fast and loose with things. That's a lot of settings. They never tried to get Christopher to attack all of these at once. That's just too many. But what they did do was use mathematical analysis and various flaws in the machine, one of the biggest ones being you never can encode, a letter would never encode as itself, and that turned out to be a humongous problem. The other one was certain words would be repeated all the time, like weather report or Heil Hitler, and they could use that as a key. So what that would do is pare that number down to a manageable size, so big that humans would not be able to do it very quickly, but that Christopher could. By the end of the war, it only took Christopher 20 minutes to break the code, and then they had the rest of the day to analyze data. All right, so everything I've been talking about so far, private key. You tell somebody what your key is, they can read all your stuff. We're going to switch and talk about public keys. The 1970s were when public key cryptography was developed. And the big three letters are RSA. That's for three mathematicians / computer scientists, Rivest, Shamir, and Edelman. And the way that it works is as follows. You take two large prime numbers, P and Q. Everybody remember prime number is one that does not factor non-trivially. Or not, oh, sorry, only factor. No, doesn't factor non-trivially. Only factors is one in itself, and it's bigger than one. And by large, in this case, I mean 100 to 200 digits. So ginormous. And I need an exponent e. If m's the plain text, c is the ciphertext, I get this by taking m to the eth power and reducing it mod that big product. You can tell everybody, you can tell all your friends and neighbors what your PQ is and what your E is. They can know exactly how you encode. But the claim is they can't figure out how to decode in practice. In theory, it's easy. If you know what P and Q are, then you can compute an exponent D that decrypts it. The ciphertext of the dth power, blah, 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 gives us our message back. So if you know P and Q, then you can decode it. And you may say, well, geez, you know, the number's 15, I can factor 5 and 3, but for big numbers, factoring is hard. Everybody believes that factoring large numbers into primes is hard. Hard like it would take billions, trillions of years to do, even with the computer. So PQ can be made public without giving away what P and Q are, and which makes your code secure. With a bit of a caveat, when they first developed this, Rivest, Shamir, and Edelman in '77 gave a challenge to the world. They took a PQ that had 129 digits, and they guesstimated that it would take 40 quadrillion years to factor PQ, so that no one would ever read their message. But in 1993, people had made progress in factorization algorithms and the idea of distributed computing. Instead of doing it on one computer, you would farm it out to, in this case, 1,600 computers. And they would all work on it simultaneously. I think it took years and years of CPU time. And the code was, the message was, the magic words are squeamish ossifrage. And ossifrage is a kind of bird. So you may think, oh, well, that's it for RSA. No, all you have to do is increase the size of P and Q, and it becomes more than even this distributed computing approach can help. Oh, so one of the nice things you can do with RSA is to sign and authenticate messages. So the sender would know, nobody but the intended receiver would get it, and the receiver knows nobody but the alleged sender could have sent it. So how does this work? Well, I have to disabuse you of one thing. You talk about encoding and decoding. Just think of them as two processes that are inverse to each other, opposite to each other. So one I'll call public, one I'll call private, and let's not worry about decrypt or encrypt. So Alice, the ubiquitous person in cryptography, wants to send a message to Bob, the other universal person in cryptography. And how is she going to, what's she going to do? She's going to use her private process. Who knows her private process? Just her, just Alice. But she can look up in the phone book and get Bob's public information. So she'll do those two. Then she calls Bob up and says, Bob, I just sent you a message. What's Bob do? How does Bob undo the public part of his code. He uses his private part. Go ahead and put it up there. So if he does his private part,
That sounds bad.
oh, sorry. I didn't think that one through, sorry. His private code. So if you do these two things, they undo each other, yes? This undoes that. So now, all I have is private A and public A, and these two will undo each other. That gives you the message. Now, how does Alice know that only Bob could have gotten it? Well, which piece of the puzzle is the only one Bob has? He has this, and nobody else has that. And how does Bob know Alice sent it? Because of this. This is not just academic falderall. This is invaluable for communicating in the open market. It's the basis, the RSA is the basis for all the buying and selling people do on the internet, at least all the secure buying and selling, involves RSA. It's also the key component of PGP, which is pretty good privacy. So if you want to keep your own stuff encrypted and maybe perhaps keep the NSA from learning about what you're doing, PGP is it. Okay, so the current status of things is it looks like ordinary computers are not going to be able to handle RSA, but there may be a fly in the ointment. There are things called quantum computers. Regular computers use bits, quantum computers use qubits. Qubits are superpositions of the classical 0 and 1 bits, just as the famous Schrodinger cat is a superposition of a live cat and a dead cat. So quantum computers can simultaneously have things be 0 and 1. The mathematician Peter Shor in '94 found that sufficiently large quantum computers could factor big numbers instantaneously. Essentially, you would have billions of little cats all simultaneously factoring things, and they end up doing it all at once. So the question arises, can a sufficiently large quantum computer be built and destroyed, and that'd be the end of RSA if such a thing could happen? What's the current status of it? So people have built very, very small quantum computers, like with 15 qubits. The current factoring record is they can factor 143 into 11 times 13. So at least for the time being, RSA is safe. And I don't know why. My personal religious belief, this just seems too good to be true. You know, you can create something where you can factor 1,000-digit numbers instantaneously. It just seems unlikely. But I don't know. I'm not a physicist, so I don't know. All right, so I think we've come almost to the end of the talk. So I think there's a parallelism here. So Turing was trying to develop a computer that will allow him to crack Enigma, and if they're ever able to invent the quantum computer, that will be the end of RSA. Do I want to say one more thing? I want to say one more thing about codes, which I just noticed in seeing the version this time. With the Soviet spy was using a Beal code, and he used a Bible. A Beal code is a very peculiar, it's a very personal kind of code where you pick some text that you're going to use as a code. You then pick words in the text that you want. So suppose I want to say help. I would find a word in the text that had the letter H as its first letter, one that had E as its first letter, one that had L as its first letter, one that had P as its first letter, and then take the number of where those were in the text. So this is based on, there's some treasure allegedly buried in the state of Virginia that the Beals buried, and they encoded a message saying where it was buried. People have been able to decrypt the first Beal cipher using the Declaration of Independence. It turns out that was the text that was used. In the movie, the Soviet spy used a passage from Matthew as the text that was used. So that's another different kind of code, which if I would have put up in a slideshow if I'd thought of it, or if I'd noticed it the first time I saw the movie. But, I have a list of references here. Don't worry about all this stuff. I've got pieces of paper with this information all on it. Because right when you have websites, it's easy to copy them down wrong. Any questions? Yes?
Have you heard of the quantum encryption that's being worked on in Washington University?
I have heard something about it.
The modification of the knapsack problem?
Oh, really? No, I had not heard that. Cool. Any other questions? Well, this is the last in the Science on Screen series. I think this is really a wonderful project, and to thank Moxie Cinema, Mike Stevens, and the Sloan Foundation for funding. Oh, sorry.
I have a question.
Yes.
I built my first computer in 1979.
Mm-hmm.
It was a 500 hertz machine
Uh-huh.
running 4 bits. And I have at home now a 4.5 gigahertz 64-bit machine, etc. And I've been watching. I was a member of the Homebrew Computer Club as well.
Mm-hmm.
And my question is, why do you, is it an act of faith on your part regarding the...
Oh, the quantum computer? Of course, it's a little bit an act of faith. It's more, what I hear is there's this problem of decoherence. It's hard to keep all of the qubits from interacting with the...
I just look at the growth, and just since 1979
Oh, no.
to now, and to me, it seems that only an act of, it's only faith could make you think that that's...
Well, no, but you're thinking about classical computers, and I'm thinking of the quantum computers. I think that, well...
I'm thinking of innovation in general.
Oh, okay. It's just more, it seems almost like, the analog for me is it seems like perpetual motion machine. It just seems like that's too good to be true. But maybe I'm wrong. I'm probably wrong.
So is multiple universes, or string theory, or, I mean, too good to be true.
That's the less
Yes.
of sciences.
Any other questions? Yes?
Can you break Beal cipher, whatever it's called, when you have the text, if you don't know what the text was?
No. No, and that's what makes Beal ciphers hard. Because if you don't know the text, you're in trouble.
Does MSU offer any courses geared in this direction?
Yes, in fact, we have a course on applied abstract algebra that deals with a lot of these topics.
Any degree programs?
Not yet. As part of our math degree, you can pick up some expertise in cryptography. Thank you very much. Thank you.